This is going to be Chapter 6, Day 1. And our objective is going to be able to evaluate energy curves and do calculations. Now, our objective actually won't even come about until about the 30th minute, so you're just going to have to kind of bear with me while we get some background stuff taken care of. First off, does anybody know what energy is? Oliver, you did the Learn Smart, I noticed. You should be able to answer this, I'm guessing. But does anybody? Ooh, we are at 26. That's a good job, guys. Anybody no one on here knows what energy is?
It's the potential to do work.
Okay, so they use the term ability, but I like them both. So let's say it's the ability to do work. Now, energy is classified two ways. What are they?
Potential and kinetic.
Potential and kinetic. Alrighty, potential and kinetic. So, somebody not named Painter, can you tell me what's the difference there? Or what the definition of potential energy is?
Potential energy is energy that is stored,
so
mostly
this is
based on position.
Stored, often due to position. So this is the rock analogy that they've used since the beginning of time. Every chemistry class I've ever taken has always used the rock at the top of the hill for the potential energy, and I think that they actually used that in the textbook, didn't they? Anybody do any of this? No, I think so. Okay. Now, kinetic, if potential is stored, kinetic is what? Nobody knows what kinetic energy is?
Released.
What?
Released energy. Energy in motion.
Okay, so I like that. Energy in motion. Okay, or action energy. Okay. Now, when you talk about these two, you need to understand something. Is that the energy of the universe is constant. And it is a mixture of potential and kinetic energy. Now, the most beneficial kind of energy to us, okay, is concentrated energy. Concentrated energy. Okay? Now, can anybody think of an example of concentrated energy? Anybody?
Still like the sun or stars?
Okay, so we're going to get to that in a minute. But like right now on Earth, real life, anybody think of an example of concentrated energy? Okay,
Burning coal.
Okay, so let's say I've got a lump of coal. I don't know who said that, but that's a good one. Wasn't where I was going, but I like it. So a lump of coal is an example of concentrated energy. Okay? In order for us to extract that energy, what do?
Burn it.
We burn it, right? So I take that coal and I burn it. Okay? I burn it. What am I doing as I burn that? Was that you, Higley? Who said burn it?
Oh, it's Higley.
Well, I just asked you that and you shook your head no.
Oh, sorry, my bad.
Okay, so by burning it, what am I really doing to it? Do you know?
It's like a chemical change.
It is. But as I burn it, I'm taking that energy and I'm going to release it, right? I'm going to release it. And in releasing it, I spread it out. Okay, now, So let's say I take that lump of coal and I burn it, right? It's going to keep me warm for a little bit, right? But eventually it's going to go out. What happened to all that energy that was stored inside it? Anybody know?
Went into like the air.
Okay, so exactly, it's still there. It went into the air, and it went into my body, and it went into the metal that was surrounding it, and whatever. And what happens is this: is that the energy, like we said, the energy of the universe is constant, but as it becomes more and more spread out, it becomes less and less useful. Because once that energy goes into the air and is spread out so much, is it of any benefit to us? It's not, okay? The only energy that is really beneficial to us is concentrated energy, okay? So for example, let's say I look at an apple. Okay, I like apples, right? So an apple is an example of concentrated energy, okay? How does that concentrated energy come to be? Anybody know how that happened?
The plant absorbs light from the sun and converts it into the molecular bonds and like sugars and stuff, and then it stores all that starch and sugars and stuff in the apple.
Okay, so that's a really, really good explanation. Can anybody do that explanation in one word?
Photosynthesis.
Yeah, photosynthesis, right? Photosynthesis. Now, photosynthesis takes the energy that the sun gives off, right? Combines that with a little bit of carbon dioxide and water and turns it into sugars, basically, right? And those sugars then are things we consume that are then used to do what? What are those sugars used to do?
Give energy?
Yeah, to give energy to my body, right? They're used to beat my heart. They're used to run my diaphragm. They're used to give me the energy to, go to school every day, things like that, okay? So what we have is all energy ultimately comes from where? Anybody know?
The sun.
The sun, right? And this, go ahead.
Well, I was just gonna say, but that's why. But it's less efficient as it goes down. I can't remember what that term is from biology, but we only can retain 10% of what we eat.
Okay, and so no, that's really important that you bring that up, because that's basically what I'm talking about here. Is the sun puts off an immense amount of energy, right? But we are only able to harness a certain amount of it, right? We use some of it, plants use some of it, right? And as that energy gets more and more spread out, it gets less and less and less useful, okay? Concentrated energy, very beneficial to us. Spread out energy, not beneficial at all. But what happens is that it's kind of like a consistent cycle, right? As I said, as I ate that apple runs my diaphragm, right? My diaphragm helps me expel carbon dioxide, correct? Well, where does that carbon dioxide go?
Back out into the air to be absorbed by a plant.
Exactly, which goes right back to photosynthesis, which is harnessed by... So it's kind of one big cycle of energy being condensed, and then typically humans take that condensed energy and we release it. And then once that energy is spread out, it's no use. So we have to have other things, thus plants typically, that kind of reharness that energy and recondense it, and it's kind of a never-ending cycle. Which is why, if you go back here, the energy of the universe is constant. It's simply changed from being useful to being non-useful. Okay? Now, from there we need to understand how this all works. Okay? Now, I'm going to write down 3 words. Does anybody know what any of those words are? I've got a little c calorie. Go ahead.
They're like units for energy?
They are units for energy. Do you know which is which?
A capital C calorie is for food, isn't it?
This is food calories. That's a food calorie. Okay, and that's exactly, I always say a uppercase C or a capital C calorie is a food calorie. A lowercase c calorie, this is a science calorie. Okay? And by definition, this is the energy required to raise 1 gram of H2O by 1 degree Celsius. Okay, that's a science calorie. Okay, does anybody know what a joule is? No? Joules and calories are similar. Okay? A joule, 1 calorie is equal to 4.184 joules. Okay? These are both science terms. This is a food term. Does anybody know the correlation between a food calorie and a science calorie?
Isn't a food calorie like 1/1000th of a science calorie?
Okay, so I go backwards. So 1
Oh.
big C calorie is equal to 1,000 little c calories. Okay? Now think about this for a second. Does anybody know what the RDA is for calorie consumption for a teenager? RDA stands for recommended daily allowance, but what's your dietary intake supposed to be? Anybody know?
2000.
2,000 calories, right? That's about standard. If you're an active, if you're an athlete, it might be 2,400 or something. But think about that. That's 2,000 big C calories. Times that by another 1,000, and that's little c calories. That's an immense amount of energy you consume every day. Which goes back to the fact that we are not very good. Somebody brought this up. We're not very good machines, right? Because as many calories as we take in, we really don't harness them very well. Okay? Now, the kind of questions you're going to run into is something like this. How many joules are in 376.4 let's say big C calories? Okay, how many joules are in 376.4 big C calories? Now, what's wrong with that? Anybody know?
We don't have a direct conversion.
Yeah, we don't have a direct conversion, so no matter what, I'm probably going to have to go where first?
Little c calories.
Yeah, so I'm going to do what? What are these called again? Anybody remember what they're called?
Hey,
What?
hey, real quick.
Yeah.
I cannot tell from your handwriting which one's lowercase and which one's uppercase. Could you underline which one is uppercase? Okay, so food calorie is uppercase.
Yes, sorry about that. Nobody ever answered this. Who remembers what these things are called?
Conversion factors.
Conversion factors, right? So what's my first conversion factor going to be?
.184 joules over 1 cal. Little
Okay,
c.
but I'm in big C's here. Don't I got to get to little c's first? You're right, but that one goes right here. That one goes there. I'm going to go what?
Numerator.
Say that again.
1,000 little c calories as the numerator, and then
1 big calorie as a denominator.
Oh, good job, Maddie Jones. You even used the right words there. Yay, you. Right, so big C cows are gone. Little C cows are gone. I do the math. I'm going to be left in joules. Somebody spit that answer out.
I believe it is 1,574,857 joules. Or
What? 1,574,000. What was the last one? 800 and what?
857.6.
0.6 joules, right? Okay, so what would be my real answer? Anybody want to take a stab at that?
Um, 1,574,000 joules.
Close. Wouldn't that 8 make that a 5, Alvin?
Oh, yeah, I didn't know that.
Okay, but what would be a better way to write that? I mean, he would be right, but wouldn't there be a better way to do that?
Notation.
What?
Scientific notation.
Yeah, what would that be in scientific notation? I can't tell who that was, but what would I have there?
1.57 times 10 to the power of 6.
That's pretty close. Anybody know what's wrong with that?
Wouldn't it be
1.574.
Actually, it'd be 1.575. Wouldn't that 8 make that a 5, right? Why do we need that 5 there?
Sig figs.
Yeah, because that value had 4 sig figs. My answer probably better have 4 sig figs, right? Alrighty, now, so let's say I do this. So alrighty, so Mr. Denton consumed a pie with 17 grams of carbs, 38 grams of fat, and 4 grams of protein. How many calories did he consume? I'm going to assume somebody besides Oliver did the Learn Smart. The only reason I know that is because I remembered seeing hers at the end. Anybody know how to do this problem?
You turn carbs, fat, and proteins to calories.
Do you know those numbers, Alden, off the top of your head?
So 1 gram of carbs is 4 calories.
Okay.
1 gram of fat is 9 calories, and 1 gram of protein is 4 calories.
Okay. It's good to there. So what I do is I just add these two together. Not those two. Sorry. I add those two together to simplify the math, right? So I go carbs and protein. So for this one, I would have had 21 grams of carb plus protein, right? I'm going to times that by what number? I'm going to times that by 4 calories per gram, right? And then wouldn't that give me the number of calories I consume due to my carbs and proteins? And then I'm going to do the same thing. I'm going to go 38 grams of fat. I'm going to times that by 9 calories per gram. And I'm going to get that. And then what am I going to do with those two values?
Add them.
Add them, right? So does somebody have the top number for me? Oh, that's easy. That's 84. No. Yeah. Isn't that 84 big C cows? Right? What's the bottom number?
342.
342 big C cows, which is going to give me
426.
426 big C calories. Yeah, that's not a pie. That may be consumed a piece of pie with 426 calories. If you can find me a pie with only 426 calories, I'll buy that sucker all day. As long as it's good, I guess.
Pie.
What?
It's a sad pie.
Yeah, I'm more into, pecan that's got 426 calories per piece. Ah, but they are so good calories. Alrighty. Now, there are a couple of things like that. What would be a good extension for a question like that? Anybody know? What would be a really good next question to ask there?
How many joules?
Yeah, they would say something like, what is that in joules or something? We're not going to do that because didn't we already do big cows to joules? We already did that once already, didn't we?
Yeah.
Yeah, so I don't even need to do that. So that's that. Alrighty, so from there, we are going to go to, now we're going to go to where we were intending to go in the first place. Energy diagrams. There are two types of energy diagrams. 27. We have all but two here. That's like a record, I think. Right? So we have 29, and there are 27 of you on here. You have to subtract 2 because I'm 2 of those 29. That's pretty good. Makes me want to take the roll and see who's being a slacker. But it'll email it to me. Alrighty, so does anybody know what two types of energy diagrams there are? Anybody read any of this? No? Okay, they're what are known as exothermic and endothermic. Does anybody know the difference? Nobody?
In exothermic, they're releasing energy, and in endothermic, they're gaining energy.
Energy released and energy absorbed. Okay. Now, where this takes us is what's called an energy diagram. They look like this. Okay, I'm going to draw them both right here side by side so we can get an idea of what they look like. Okay, these are my two energy diagrams. Alrighty, now what we've got is this. Over here on this axis, this is the energy axis. Energy axis. Across the bottom, they call this the reaction coordinate. Okay, I usually just say, consider that kind of like time. Okay, I don't know what they really mean. I guess that just means where you're at that time. Okay, reaction coordinate. Now, this is what happens here. You need to make sure you understand this. You always start right here. You would have your reactants. Okay, obviously down here you're going to have your what?
Products.
These are going to be your products, right? So I got my products, got my reactants, and I've got my products. Okay, this difference right here, this is called delta H. Okay, the change in energy, that's what delta H stands for. And for this, it's going to be negative, which tells me that my energy was what? Anybody know what that negative tells me? Lost, which means the energy went where? If it's lost, it means it leaves the reaction and goes into the surroundings, right? Which tells me that this is what kind of reaction?
Exothermic.
This is exo. Okay, which by default then means this is endo. Okay, now right here, this right here, this is E sub A. This one, it's much bigger. This is E sub A. E sub A. That is what is referred to as the activation energy. Okay? Now, in this example, I'm going to build a fire, right? And I'm going to throw a bunch of logs on there, and because I'm a cheater, I'm probably going to dump some gas on there. And when I do that, does it just immediately burst into flames? Would my pile of sticks and gasoline just burst into flames?
No, it
Why,
wouldn't.
why not?
Because you need heat. You need activation energy.
Exactly. I got to get it started, right? So in that example, this activation energy, the distance from there to there, that amount of energy would be supplied by my what? What would supply that energy to get it going?
Like your initial spark.
Yeah, so like, for lack of a better term, that would be what the match does. The match gets it going. And then once it starts, it's going to continually burn and burn and burn until I run out of fuel, right? Until my log burns or whatever, right? And down here, I'm left with nothing but ashes, right? Now, obviously, my ashes are not near as beneficial as that piece of wood was, right? Because the ashes are basically the byproduct of all that energy being released into the surroundings. Okay? Now, if you look on the other one, if I look over here, now, let's say this is my, let's say that this is my, let's use the apple analogy. Okay, over here, I have an apple. Okay, over here I had ashes. They weren't very beneficial, right? Over here I've got an apple though, right? Now that apple, as we talked about, is an amount of stored energy, right? So what happens is the sun and water and carbon dioxide get this sucker going, right? And that tree grows and it produces that apple. And obviously that apple has an amount of energy stored in it that then I will go and eat and release that energy. Well, notice that it takes a lot of energy here for photosynthesis to occur. Most of that energy, like we said, comes from the sun. But it's one way of storing or taking some of that energy that's been spread out by us and collecting it back together again and storing it in the form of an apple or a peach or a pear. It doesn't matter what it is. We could go as far to say, well, I like to eat steak, right? Well, that steak came from a cow. Well, that cow still had to eat plants to grow, yada, yada, yada. One thing leads to another. It's the same idea, okay? So I've got an exothermic reaction and I've got an endothermic reaction. Now, what you're going to see on the test, you're going to see some of these, but the kind of question that I'm the most concerned about on the test is this. Okay, now I'm going to balance this to make this easier. Okay, now here's an equation. Okay, and they're going to tell you that delta H is equal to negative 412.7 kilojoules per mole. Now you need to make sure you understand what this means. Okay, now this should look familiar. Balanced reaction, we did this last chapter. Now, pay attention to this. Does anybody know what that tells me about that reaction? Anybody know?
Exothermic.
What?
It's exothermic.
How do you know it's exothermic?
The delta H is negative.
Delta H is negative. I know this is exothermic. Energy is going to be released. Okay? Now, this is what the question is going to look like. Okay? Now, how much let's say I went with burning. So let's say I want to burn 4 moles of this. Okay? And I want you to tell me how much energy is released. Okay? And notice, this right here is not written in reference to the coefficients of the equation. It is simply negative 412.7 kilojoules per mole. So for every 1 mole of this I burn, I'm going to get out that much energy. Okay? So the question says, how much energy would be released by burning 4 moles of that? So I'm going to start with 4 moles of C7H6O2. How am I going to do this problem? Anybody know? Well, don't I got to get rid of my moles here? Don't I want to get into how much energy, let's say in kilojoules, because that's what I'm written in, right? Wouldn't I go negative 412.7 kilojoules for every 1 mole of C7H6O2? Then wouldn't my moles of C7H6O2 go away? I'm going to be left with what? Here. What's this answer going to be? Put it into sig figs for me as you do it. Somebody's got to know how to do this.
Would it be 800 kilojoules per mole?
That's supposed to be a kJ.
Because 412.7 times 2 is 825. And because it's just 4 moles, you only have one.
Okay, so let's do this. Let's go 4.00 moles. Good point. Yeah. Let's go 4.00 moles.
Then it would be 825.
Check your math, Evans. Check your math, Evans. And remember what I said. This is not using the coefficients. This is per mole. Now, I realize that equation's written for 2 moles to balance it, but that's not what this says. Do you see what I'm saying?
Yeah. Yeah, so it'd be negative 1,650 kilojoules per mole.
Isn't it 0.8?
Yeah.
Wouldn't that 8 make that a 1?
Yes.
Right? Now, is it kilojoules per mole or just kilojoules?
Wouldn't it be 1,650 because there's only 3 sig figs?
Yeah, but I'm going to round it to this. I'm going to round it. Oh, only 3 sig figs? Oh, yeah, because I changed it, didn't I? Yeah, sorry. Good job. Yep, you're right. I forgot I changed this from what I did in my last class. So now look. It's just in kilojoules because my moles reduced out, Evans. You see what I'm saying? Now, let me tell you what the answer is. That's the answer. Anybody figure out why that's the answer and what the difference is?
You can't release negative energy.
Exactly. So whenever they use the term released, it will always be a positive number. Always. No matter what. Okay? So the minute they use the term released, that answer is positive. No matter what. Ah!
icon things.
I'm not sure what happened. Are you guys still there? That was weird. It just kind of kicked me out. We all still here? I'm hoping that's a yes. I'm getting no comments. Are we all still here? Now it won't let me present. Here we go. Can you guys still hear me? Can you guys see my screen again? Somebody's got to talk to me. Anybody? Nobody? Can nobody hear me? No, I'm froze up. Can anybody hear me? Nobody hear me? Can anybody hear me? Can nobody hear me? Nobody can hear me.